Okay, let's go for the next experiment. This time we have diffraction grating. Diffraction grating is used mainly in spectroscopy, right, to find the wavelength, right, of a sample of gas, let's say hydrogen, helium, correct, and separate these wavelengths that usually are very close, right, and find the value for the wavelengths for gases. Okay, so that's the main use for diffraction grating, again in spectroscopy, to find the spectrum. Perfect. Let's see how it works. We have a diffraction grating. Usually in spectroscopy, the diffraction grating, right, has let's say 15,000 or 20,000 slits per inch, right? In this case, we don't have those diffraction grating, right? There are a little bit with less slits, right? But the effect is the same. Okay, great. How it works? Well, we have slits, the same thing as interference, correct? When we have double slits, right here we have a lot. And all of these slits behaves as a source, right? And then they interfere to create these bright fringes, right? Bright fringes and dark fringes too, but we pay attention on the bright fringes, correct? So this is more or less what is happening. We have the slits, and all of them, right, contribute to form, right, the bright fringes. We are only showing, right, 2 cases, right, but the rest behaves in the same way, correct? Let's take the center to be m equals 0, right? This is the order number. And then let's go to, let's say, the next one, m equals 1, m equals 2, right? Going up and going down, the same thing. M equals 1, m equals 2, and so on. Okay, this is the screen, this is the diffraction grating, and the distance from the center, right, to any point in position, we call it y. The distance between the diffraction grating and the screen is L. In this case, is 5 meters. And the equation for a diffraction grating is the same as for interference, gonna be d sine theta equals to m lambda. In this particular case, the angle is small. When the angle is small, right, we know that we can make this approximation, sine theta about tangent theta, correct? When that happens, we use tangent, and tangent, we're gonna make an angle right here to make a right triangle, gonna be y over L. Right, when we apply this this condition right here, right, gonna be then y over L equals to d, well, in this case d, the distance between 2 slits, times y, right, from the center to any bright fringe, divided by L, which is fixed. Right, gonna be m, and remember it's the order number, okay, for in this case constructive interference or bright fringes, times the wavelength of the source. In this case, it's going to be a laser. The wavelength for this laser, that we call it the theoretical value, is going to be 532, right, nanometers. Today, let's find the experimental lambda, right? When we solve from here, from lambda, it's found to be dy over ml. Perfect. Now let's do this experiment to find again a lambda and compare that to the theoretical value. Perfect. We have 3 cases. Okay, we have this diffraction grating with this is the diffraction grating, to make sure that you are familiar to this diffraction grating. We have 3 different diffraction gratings, correct? Okay, let's take the case when D1 is 0.15 millimeters. And let's take 2 parts. Let's take part A and part B. Part A, let's make m equals 1, right? And then find the distance from the center to that fringe, bright fringe, right? And let's label y1 equals something in millimeters. Okay, it's coming in this way. Imagine that this is the pattern that we get from this diffraction grating. Let's go to the center one, right? The center one, let's label it as m equals 0, right? Let's go to the first one, m equals 1. Let's take again the center. It goes from center to center, correct? And the distance from this center to the next center is going to be y1 because it's for m equals 1, and y2 for m equals 2, and so on, in that way. Correct? So taking that value, let's find the experimental lambda using this formula. Right, and then let's find the percent error. The percent error, usually we use this notation. Gonna be percent error equals to the lambda theoretical minus lambda experimental absolute value. We use absolute value to avoid negative signs, divided by the theoretical value times 100%. Okay, let's use this formula of the percent error for all of these cases. Correct? Okay, let's go to part B. M equals 2, the same thing. Let's find the distance from the center to m equals 2, right, in millimeters. Later you have to convert it to meters. Correct? Let's find the experimental value in meters. Also, remember, we can convert this into meters too. Correct? Yes. Great. And then find the percent error. Repeat the same thing, right, for case 2. Now gonna be the distance between two slits, gonna be 0.25 millimeters, and finally the last one is gonna be 0.125 millimeters. Okay, and repeat for m equals 1, for m equals 2, find this data, write the same thing in the last case. Correct? So in this experiment, you are supposed to find y1, y2 for each case. Remember, when we use, for example, part B, it says m equals 2, meaning that in the formula you are supposed to substitute m by 2, right? D2 or D is given, in this case is this one, but for part B, m takes the value of 2. Of course, for part 1 or part A, m equals 1, and so on. So it depends, again, the number of fringe, right, the order number that you want to use. In this case, we have only 2. We can use more, of course. We can use m equals 5, 6, and so on. But this is enough, right, for this experiment. Now let's do the measurement of y1 and y2 for these 3 cases. Okay, let's do it. Okay, let's go for case 1. Okay, now case 2. Okay, now let's go for case 3. Okay, please do all the measurement and do the calculations, and see you in the next experiment. Bye.